we will consider a rectangular loop in a uniform magnetic field. We will find that the total force on the loop is 0, but that there is a torque that tends to turn the loop to a particular orientation with respect to the field. We've got a loop. The axis of rotation is here. This is the way it's turning, and you can see that there's a force pulling the top part of this loop that way, and there's another force pulling it that way. So you've got a torque occurring there. Now you've got a force in this direction and a force in that direction. Well, they're cancelling each other out. The unit normal, the vector A here, there's the plane, and that's coming out of the plane. So that's there. That makes an angle, theta, with the magnetic field. See, the magnetic fields are all going in this direction. You can see that the lines of action here, when we want to work out torques, we've got the line of action here, the line of action here. Now we know that when we only have to work out one of the F time, torque equals F times L. So we need to find the perpendicular distance between the lines of action, and that perpendicular is B sine alpha. So what else in this diagram? Yeah, we've set this point here to the center of this axis. We've set it to start. We're calling that the origin. The X is going that way, the Z going up, and the Y is going along the axis here. Yeah. So that's, I think, everything in the diagram. So let's go through the notes. Right. This rectangular loop of wire has sides of length A and B. There's B and there's A. The normal of the plane makes an angle alpha with the direction of a uniform magnetic field. So there's the uniform magnetic field going up. That's the angle alpha between the unit normal and this beta field going up. Force F on the right side, this force F, is F equals IAB. Remember, we're going to use this. In this case, L is A, because that length here is A. So that's A. So the force F on the right side, this force F, has a magnitude of FIAB. A force of the same magnitude acts on the opposite side, so this force is the same magnitude as that. So if you add the force together, you get 0. Now the forces on the sides, this F dash and this minus F dash, represented by vectors F dash and minus F dash, have magnitudes IB sine 90. Alright, so now look, we're not at right angles now. The B and the I here are at right angles, but here we have to allow for that angle here. Okay, so we end up with IB sine 90 minus alpha. But it's kind of irrelevant really, because the total force through the y-axis is 0, because that force equals that one, and also because these forces lie in the same line of action, we haven't got this displacement like we have here, then there's no torque. The forces cancel and there's no torque. Moving on to this box 2, the two forces F and F, so this force and this force, constitute a couple, as we've said, that the torque of a couple has the same value with respect to any point and is given by the magnitude of either force multiplied by the distance between the lines of action of the two forces. From the diagram, this distance is B sine alpha. So I said that we drop this perpendicular and we've got the moment of the torque, which is B sine alpha. So the torque, the force is IBA rather, and that's the force, and then the length is B sine alpha. So that gives us equation 1. Right, it says here, remember torque is force times perpendicular distance between lines of action. The torque is greatest when alpha equals 90, when plane of the chord is parallel to the field. It is 0 when alpha equals 0 or 180. So yeah, so when it's this, or even when it's that, it's all the way around, then torque is 0. You can see I've just drawn this as if it's spun up. So B sine 90, so sine 90 in this case is 1, so that distance then is B when there's maximum torque. Since A times B is the area of this whole loop, equation 1, this equation here, may also be written as torque equals IBA sine alpha. So we can rewrite this as this. because we know that the area is A times B. The product here, I and A, the product IA is called the magnetic moment. They've given it a name. They've defined that as a magnetic moment. So we say mu equals I times A is the magnetic moment. So torque on a magnetic moment associated with a current loop can be expressed simply as torque equals the magnetic moment times the magnetic field B times the angle between them, sine alpha. So we'd often use that equation. So we have magnitude of torque is, as I said before, T equals mu B sine alpha. Because of the directional relations above, the torque tends to rotate loop in a direction of decreasing alpha. So we've got a force pulling it that way. This vector mu wants to move from that position to that position. And so the angle is decreasing. I'll just repeat that. Because of the directional relations above, the torque tends to rotate loop in direction of decreasing alpha towards its equilibrium position perpendicular to direction of magnetic field B. Basically, it's that is trying to point, that will try and get to that position where the torque effectively is zero. Then, you know, because the force are in the same lines of action that way and that way. So vector torque, we can express this more compactly in terms of vector torque. First, define a vector area A having magnitude A and direction perpendicular to its plane, i.e. unit normal to the plane. Then, as equation 2 and in the diagram show, the vector torque is given by torque IA cross B. Right, okay, so that's the equation 2. What we're talking about in the diagram there is we're displaying the torque. So if it's A cross B, let's quickly go back to the diagram again. This is the A vector here, remember, this is the normal vector to the plane, yeah? And this is the magnetic vector going in this direction, and that's the angle between them. So if we A cross B, then we're going like that. So if we're going in that direction, then you can see it's along the axis, and I've marked that as the torque, yeah? So that torque is along that axis there. So in the diagram, the shows the vector torque is given by torque IA cross B. We can also define a vector magnetic moment, U equals IA. So in terms of the vector mu, we can express the torque simply as torque equals mu, the vector mu, cross B, yeah? Taking magnitude of this cross product gives us equation 2. So if we take the magnitude of that, we get back to this, okay? So that's nice. And all we got to do is just remember that mu is I times A. This equation here is an analogue of the torque equals the dipole moment crossed with electric field vector. That's the reason we've defined this vector torque, yeah? Just so we can get that in the same form as that. It nicely matches up torques which are dealing with magnetic fields and torques that are dealing with electric fields. It's a very nice correspondence.